Hello. In this video I want to talk about momentum in collisions with two objects. So far we've seen in experimental data that makes us believe or see that the total momentum before and after collision is the same. You guys did some work around this idea of impulse, where a force acting on an object for some period of time results in changing that object's momentum. Today we're going to come back to this idea about the conservation of momentum, which is that the total momentum in a system stays constant. So in that experiment we looked at, we could see experimentally that was the case. We can also actually prove it using Newton's third law. So that's what I'm going to go through right now. So during a collision or interaction between two objects, we have to agree that each object is touching each other for the same amount of time, delta t, and that the forces acting on each other are the same size but in opposite direction, which is Newton's third law. And using those two ideas, we can come up with conservation momentum. So here's the equation for impulse. So change in momentum is force times change in time. And here's a diagram. Object 1 is coming to the right, object 2 is going to the left. They're going to interact, and when they do, the force of 1 on 2 will be the same but opposite of force 2 on 1. So this is Newton's third law. And then I've written out the impulse equation for each object here. Now, if we take this one, and if we say F1 delta t is the same as this, because F1 is the same as negative F2. So instead of writing F1, I'm going to go negative F2. So F1 delta t equals negative F2 delta t. And this, as we can see, is delta P1. And this is negative delta P2. So this is a pretty important statement. It's saying how much one object's momentum changes is equal and opposite to how much the other object's momentum changes. And if we move delta P2 to this side, we see that the total amount of change of momentum in a system is 0. And that's the same thing as saying conservation of momentum. And we can write this out in terms of masses and velocities. So the change in momentum of object 1 is m1 v1 prime minus m1 v1. Now this is I'm sure this is a new thing to most people. This apostrophe, it's called prime. That's what we say, prime. And it means after. So this is the momentum after, this is the momentum before of object 1. This is the momentum after of object 2. This is the momentum of object 2 before. So from this, we have three, I'd say, important equations for conservation of momentum. Three equations, I mean, it's all saying the same thing, but there's three ways of thinking about it. So one is, whatever one object's momentum changes, the other object will be equal and opposite in momentum change. We can say that the total momentum change is always 0. And then the third way to write out is kind of rewriting this one a little bit. And I'm just going to group the m1v1 and the m2v2 on one side, and I'll put the primes on the other side, so it looks like this. So this is the total momentum before the collision, and this is the total momentum after the collision. Oops, 2. Okay, so let's try a problem here. This is a problem involving two balls hitting each other, and we're given some information. So what I can do is write down the stuff we know and then use these equations of conservation of momentum to try to figure out the missing stuff. So I'm going to say the white ball is going to be M1, and I'm going to call the black ball to be M2. So M1 is 0.2 kilograms. It's traveling with some momentum, so we know P1 is 5 kilograms meters per second. And we know after the collision, the velocity comes to a stop. So V1 prime is 0. For object 2, we have M2 is 0.1 kilograms. Stationary ball, so that means V2 is 0. And we're looking for V2 prime. And we're also looking for the delta P1, delta P2. All right, so let's check this out. I know that V1 prime is 0, therefore P1 prime has to be 0. If it's not moving afterwards, that means its momentum afterwards is 0. And we also know delta P1 now, because delta P1 it was going 5, goes to 0. That means its change is -5 kilogram meters per second. So that's object number 1. Object number 2, well, we know that P2 is 0 because V2 is 0. So it's starting at rest. That means its initial momentum was at rest. And if delta P1 is 5 or -5, that means delta P2 has to be the same size, right there, this equation, same size, but opposite. So this is +5. So now we can figure out the P2 prime. So if it started at 0 and it changes by 5, therefore P2 prime must be +5 kilogram meters per second. And finally, we're looking for its velocity. So P2 prime equals M2 V2 prime. So V2 prime is the momentum divided by mass. So it's 5 divided by 0.1, 50 meters per second. So super fast. All right. Just a little statement here about where this law applies. Well, I mean, it always applies. It's a universal law. The way we analyze it, we're going to analyze it in closed, isolated systems. So that means we're going to evaluate or solve problems where the system consists of two particles or two objects, and there's, other than those two objects interacting with each other, there's no other forces acting on those objects, and no momentum's transferring in and out of the system. So this is just a way to make our analysis more simple. So here's another problem. The physics of it is pretty straightforward. The math starts to kind of get more, it's not really confusing, but there's more algebra. There's a lot of variables to move around. The question is 0.26 kilogram cue ball. It's moving with some speed east, collides head on with another ball that's traveling west, and after the collision, the cue ball is traveling west at a new speed, and we want to know the velocity of the 8 ball. So it's actually very similar to the question we just did. So the way I go about this is I write down everything I know. So I know my two masses, and I know my two initial velocities. And then afterwards, I know the velocity of the cue ball. And I'm looking for the velocity of the 8 ball afterwards. A couple things I do to help out with this. I'm being really clear. I'm going to say which direction is positive. I'm calling east positive. That's why this is a positive, because we said it's east. And this is a negative number because it's traveling west. So these are kind of important things you should be really clear on when you set up your problems. What object is which? So I'm calling the 1 to be the cue ball. I'm calling 2 to be the 8 ball. And what direction is positive? Okay, to solve the problem, I'm using the conservation of momentum equation. P1 plus P2 is equal to P1 prime plus P2 prime. So that's this equation here. Same as this. And we know a whole bunch of stuff here. We know the M's, we know V1, we know V2, and we know V1 prime. So we're just solving this equation for that variable. And that's what I did here. I solve it algebraically. I move this term over to this side first, and then I divide both sides by M2. And I get this equation here. I plug in all those numbers we know, and I get a V2 prime of 6.27 meters per second. So the math looks kind of complicated because there's so many little things, but it's pretty, in one sense, it's pretty straightforward. There's another way to think about this as well. This is we can think of it in terms of, instead of using this equation in terms of adding up all the momentums, we can think about it in terms of changing momentums. So we know everything about object number 1. We know its mass, and we know its beginning velocity and final velocity. So we can find out delta P1. So delta P1 is its final momentum subtracting the initial momentum. And plugging in those numbers, I get a delta P1 of negative 1.69. Therefore, we know that delta P2 is equal and opposite to that. So we're using this idea. So we know delta P2, and we already know that we know what P2 is, because we knew its mass and its initial velocity. So we can find out delta P2 prime, or sorry, we can figure out P2 prime that way, and we get the same answer. Mathematically, actually, it works out to be exactly the same. It's just a slightly different way at looking at how you want to solve the problem. Okay, I think that's enough to get you started on some practice problems. Good luck.